All right, the next topic we're going to look at in terms of electrophilic aromatic substitution is sulfonation. So let's take a look at the overall reaction for sulfonation. Again, we're going to start with an aromatic compound. In this case, I'm just going to use benzene. And the reagent we're going to use for sulfonation is called fuming sulfuric acid. So we'll just write down fuming H2SO4, that's sulfuric acid. And when this reaction is complete, what you'll be left with is a molecule that again is substituted. And this functional group is called a sulfonic acid. All right, so then the question is, well, what does fuming mean? A lot of students think that this just means hot sulfuric acid. That's actually not the case. So let's take a look. So fuming H2SO4 sulfuric acid has sulfur trioxide added. All right, so the question is, well, why are they adding sulfur trioxide? Well, in this case, sulfur trioxide can be drawn a few different ways. Sometimes you see it in this form. However, there's also a major resonance contributor where oxygen can carry a negative charge. And it's important to know that really each of the three oxygens is carrying that charge, not just one of them. So each oxygen can carry a partial charge. And we can show it using a variety of different resonance structures, but this would be the major contributor. The reason that this is a major contributor is that the p orbitals forming that pi bond between sulfur and oxygen are size mismatched. Sulfur is much, much, much bigger, so that pi bond is relatively weak, and therefore the oxygen carries a large amount of negative character with it. So this is fuming sulfuric acid. Just means it has that sulfur trioxide added. And what makes this unique is that this sulfur right here is super electrophilic. It desperately wants electrons. So this is a great electrophile. All right, so let's see how this works in the mechanism. The mechanism is going to be a little bit different than what we saw in the previous video. Instead of a Lewis acid-base reaction, we're just going to start immediately with our aromatic ring. In this case, our aromatic ring is a really weak nucleophile, but that's okay because we're going to be reacting it with a strong electrophile. That's the sulfur trioxide. So I'm going to go ahead and draw out the sulfur trioxide like this and just indicate that it is a really good electrophile. So if you don't have a good nucleophile, the only way to get around it is to use an even stronger electrophile. So this pi bond from our aromatic ring is going to attack sulfur and kick electrons up to oxygen. And again, we're going to break aromaticity and we're going to form our rhenium ion. So in this case, we're going to have sulfur double bonded to two oxygens, and then a single bond to our third oxygen. In this case, it's important to note that we have a positive charge, so we should show that positive charge on the carbon with one hydrogen. And then in the next step, what we're going to do is we're going to either do a proton transfer or restore aromaticity. It really doesn't matter which one occurs first. They're both very fast, so I'm just going to go ahead and show the proton transfer. So this reaction's done in sulfuric acid, really strong acid, so it's going to quickly reprotonate. We still have this positive charge here. Now we've got our sulfonic acid group protonated. And then next, what we have is the conjugate base participating in the reaction where we restore aromaticity. So up above here, this acid is going to give us this conjugate base, and it's going to help us by grabbing this proton and then clamping down. So when we do this reaction, we're going to restore aromaticity, and we're going to end up with our neutral product and sulfuric acid. So when we think about sulfuric acid in this reaction, what is its role? Well, in this case, it's really just acting as a solvent for this reaction. The reagent that we're really concerned about is this sulfur trioxide. This is the active reagent for the reaction. The sulfuric acid is just acting as a solvent and helping us move protons around. All right, so I'll show you a really cool trick with this reaction. And we'll talk more about this later when we get into synthesis problems. But this cool trick is that this reaction is reversible. So let's go ahead and show the forward reaction. So I'm going to do H2SO4. And in this case, you can write SO3 or fuming. I'll understand either way. And we can show the forward reaction. We can even abbreviate that group by just saying SO3H. That's our sulfonic acid. If we want to go in the reverse reaction, it's really straightforward. All we need to do is react this with dilute sulfuric acid. So what does that mean? It means that we're just going to run this in sulfuric acid and water, and we can remove that. So the question is, why might you want to do this? Well, there's a few reasons. One is you could treat this as a protecting group. Another way to describe this is a blocking group. And what that means is by installing the sulfonic acid in that position, you block that carbon from doing further chemistry until you remove it later on. And so we'll look at that with some synthesis problems later. All right, so the second reaction I wanted to finish up with is nitration. Nitration is a really neat reaction. So let's quickly go over that. Again, let's take a look at the overall reaction before we jump into the mechanism. So, this works with any aromatic molecule, but we're going to use benzene as just our classic example. And we're going to use HNO3, that's nitric acid, and then H2SO4, that's sulfuric acid. When we do this reaction, you can install a nitro group. And a nitro group is zwitterionic by nature. And when we think about it, the oxygen with the negative charge has resonance with the other oxygen. So really both oxygens are going to carry that negative charge, but you can show it as a zwitterionic form if you'd like. All right, so I'll show you the mechanism for this, and then we'll take a look at a cool example. The mechanism for this one is a little bit different than what we've seen before. We're going to first do an acid-base reaction. Like I've said before in class, acid-base chemistry is really, really fast. One of the fastest reactions in chemistry. And in this case, we've got a very strong acid, sulfuric acid. And sulfuric acid, in this case, is much more acidic than nitric acid. So it will actually protonate nitric acid. So nitric acid will steal this proton. And we'll have this good leaving group over here. Now some students will ask, why did we protonate this oxygen and not this oxygen? The reality is both could be protonated. However, if we protonated the green highlighted oxygen, it doesn't take us in a useful direction. So I'll show you why the yellow highlighted oxygen if it gets protonated, it takes us in a useful direction. The next step involves kicking that entire group off. So this group right here is an amazing leaving group. We saw this before when we were doing substitution and elimination chemistry. If we protonated the other oxygen, we wouldn't have a leaving group to kick off. All right, so now let's take a look at our next intermediates. We now have nitrogen that's double bonded to 2 oxygens, and we kicked off water as our leaving group up above, right? So that's going to be our second product. All right, this intermediate that we've formed is called a nitrosonium ion. It's a really good electrophile. Just like we saw in the sulfonation reaction, benzene isn't a very good nucleophile, so the only way to get around that is to have a really good electrophile. So in the next step, what we're going to do is we're going to treat this with our aromatic ring, in this case benzene. Like we said, it's a weak nucleophile, but that's okay. We've got a strong electrophile. So I'm going to have this attack the nitrogen with a positive charge and kick electrons over to oxygen. All right, so we're almost there. Again, we're going to form this uranium ion. And this uranium ion is a key feature of any of these electrophilic aromatic substitution reactions. So we do have to break aromaticity, but that's okay because we have water floating around that was kicked off in that previous step. And water can help restore aromaticity by grabbing this proton and clamping down. And we get our full nitro group installed along with the conjugate acid, which in this case would just be the hydronium ion. All right, so let's see some examples of this. I'll show you the most common example, and that is using this aromatic molecule. And if you remember back to last term, the name of this compound is toluene, or methylbenzene. Most people just call it toluene. And if we treat this with nitric acid and sulfuric acid in excess, you can actually get multiple nitrations to occur. In particular, we're going to nitrate the ortho and the para positions relative to that methyl group. We'll talk more about that later, but that's due to the activating nature of that methyl substituent. All right, so let's take a look at what we get out there. We'll get 3 nitro groups installed. And so this would be called 2, 4, let me do the numbering right. 2, 3, 4, 5, 6. So 2, 4, 6 trinitrotoluene, also known as TNT, the explosive. So this is how a lot of these high explosives are made, is actually through a nitration reaction. The more nitrogens that you have in an organic compound relative to carbon, the more explosive the compound tends to be. All right, so just like with sulfonation, there's another cool trick you can do with this one. Again, this is useful for synthesis problems later on. The cool trick is, if you have an aromatic ring, you can treat this with nitric acid and sulfuric acid to install your nitro group. So we'll get this nitro group on there. And then if you treat this with HCl, hydrochloric acid, and some sort of metal like iron or zinc, you can do a reduction reaction. And this reduction reaction will convert that nitro group into an amine. And if you remember, this is an aniline. So this is a really useful way for converting a nitro group to an amine, and we'll discuss this reaction in a lot more detail later on, but this is quite versatile when you're doing synthesis problems. All right, so that's where we're going to stop today. For tomorrow's video, we'll look at Friedel-Crafts alkylation and Friedel-Crafts acylation reactions.